Okay, so continuing our conversation about chemical nomenclature, this is just a brief conversation about how we go about naming compounds. So when I go into naming a compound and I look at a new compound, I ask myself two questions. Is there a metal? And if there is a metal, do we always know the charge of that metal? Now, of course, I put an asterisk there. The asterisk is a metal or H plus as a cation when we have an acid, or a polyatomic cation, one of which is ammonia, NH4 plus, that we might see. So those are species without metals that can form ionic species or acids. But usually we see an ionic species from the presence of a metal, and we see molecular species with nonmetals. We have a couple of choices if we know the charge on the metal or not. If we know always the charge, we don't have to indicate the charge of the metal. If we don't always know the charge of the cation, then we put it in Roman numerals in parentheses after the name of the metal. So make sure you know where the metals are on the periodic table. And there is a video review of locating the metals, but they're here in yellow. And recall that when we are putting ions together, the charges have to sum to zero. The positive charges of the electrons lost must equal the negative charges of the electrons gained. So make sure that you have gone through the review if you're unsure about that. So if we have a metal, yes, and we know its charge, magnesium is always magnesium 2 plus. So make sure you review how to identify metals and their charges in the previous assignments. And nitride is always 3 minus. So we would combine them 3 and 2 because they have a 6 plus common denominator. So Mg 3 and 2. And this is magnesium nitride. Iodide and cadmium. So cadmium is a metal. Yes. Do we know its charge? Yes. It's a transition metal, but it's always 2 plus. The halogens like iodide are always 1 minus. So we're going to need 2 of those iodide 1 minuses to balance the cadmium 2 plus. We'll always put the metal first, even if we're given the elements in out of order. We'll put the metal first in our formula, and we'll need 2 iodides to make cadmium iodide. And remember, with all of our nomenclature, the suffix on the base of the anion or the second element for molecules becomes "ide." So this is cadmium iodide. And when we know the ionic species charge of the metal, it's the only change that we make is to the suffix of the anion. Calcium and oxygen together, calcium is 2 plus, oxygen is 2 minus. Calcium is a metal. It's an alkaline earth metal, always with a 2 plus charge. And so to name it, we just place the name of the metal, calcium, and then the base of the anion and ide, so that's oxide. And with aluminum and chlorine, is there a metal? Yes, aluminum. Do we know its charge? Yes, aluminum is always 3 plus. So this would then be aluminum. Chlorine, except the suffix becomes ide, so this is chloride. aluminum chloride. So that's for the case when we have a metal and we know the charge of the metal. But these elements in yellow represent metals that we do not always know what type of cation they're going to form, what charge of cation they're going to form. And as a result, we use parentheses after the metal's name to indicate how many electrons that metal has lost, or the positive charge of the cation. And then we put the anion's name with the suffix "ide." So we're going to use our knowledge about the charge of the anion to deduce what the charge of our metal that has a mysterious cation charge. So here tin is one of the metals that we do not know its charge, but fluorine is always, as fluoride, F minus, and there's two of them. So F minus, two of them, means we have a 2 minus charge here, which means we must have a 2 plus charge in tin, which means that tin must be 2 plus because there's only one tin present. And so we're going to have tin, open parentheses, the charge of the metal in Roman numerals, it's 2 plus, so II, and fluor and the suffix "ide." Fluoride. Tin 2 fluoride. All right. So we have cobalt. Cobalt is a metal. It's a transition metal, and we do not always know the charge of cobalt. So we're going to look to sulfur. Sulfur in group 16 or 6A always has a 2 minus charge. And so if sulfur is 2 minus and there's one sulfide, then cobalt must be 2 plus for the charges to sum to 0. So that means that this one cobalt must have the charge of 2 plus. So then naming this species, we put the metal's name, cobalt. The Roman numerals then for 2 plus, II, and sulfur, but we'll put the suffix as "ide," sulfide, IDE. Chromium with 3 iodines. So chromium is a metal. It's a transition metal and not silver, cadmium, or zinc, those 3 transition metals that we know the charge of. And so we're going to use the Roman numerals in the parentheses to tell us what the charge of the metal is. Well, how do we know the charge? Well, it's this metal cation is being countered by 3 iodines, and iodine is always 1 minus as a halogen in group 17 or 7A. And if we have 3 of them, and our 1 chromium is balancing out this 3 minus charge, then our chromium must be 3 plus for the charges to sum to 0. And so if we have 1 chromium and 3 iodines, and the iodines are all 1 minus, the chromium must be 3 plus. So the name of this species is chromium 3. So the Roman numeral for 3, because that's the charge of the metal cation. And then iodine, but with the "ide," so it becomes iodide. IDE, iodide. Chromium 3 iodide. So that's what happens when a metal gives up an electron to another element like sulfur or iodine to complete the ionic transfer. But sometimes a metal can give up an electron and donate it to a molecule, which then gains the electron and forms what we call a polyatomic many-atom ion rather than a monoatomic ion. Polyatomic ions have unique names for each species. These are some common polyatomic ions. You can see that we have a few polyatomic cations, positively charged species, but far more negatively charged species, polyatomic anions, which are common in chemistry. We're going to need to learn the names. The names have some patterns, which we'll talk about to help us remember some of them and some little tricks, but for the most part, this is a process that repetition and note cards can help us really start to master, practice, like in the upcoming assignment. A lot of the species of polyatomic anions contain oxygen. They're called oxyanions. Oxyanions are so common and plentiful that they have a nomenclature system in which the suffixes relate to how many oxygens there are, with the suffix "ite" meaning less oxygens and "ate" meaning more oxygens, and then further prefixes, hypo meaning less than the "ite" number of oxygens, and per meaning more than the "ate" number of oxygens. So 1 oxygen in the chlorate series is hypochlorite, 2 oxygens is chlorite, 3 oxygens is chlorate, 4 oxygens is perchlorate. In the sulfate series here, sulfate has 4 oxygens, less than that. Sulfite has 3 oxygens. In these oxyanion series, the charge stays the same. It's just the number of oxygens. But ultimately, this is a series of species that we just need to memorize because they are so common. Within the nomenclature and naming them, all we have to do is drop their name in. There's no changing of the suffix, prefix. We just name them as is. So a couple examples. Household bleach is sodium hypochlorite. So hypochlorite is the polyatomic ion ClO minus. Sodium always forms an Na plus, a 1 plus as an alkali metal. So sodium hypochlorite or bleach is NaClO. Just 1 hypochlorite and 1 sodium. Ammonium phosphate, so 2 polyatomic ions here, a cation and an anion. Ammonium here is NH4 plus. Phosphate is all the way over here, PO4 3 minus. Ammonium phosphate is found in plant food, like Miracle-Gro. So we have 1 plus and 3 minus. So we're going to need 3 ammonium to balance out our 3 minus charge of phosphate. So open parentheses, and we're going to have NH4 3 times with our 1 PO4 3 minus. And this then is ammonium phosphate. So drain cleaner, like shown here, is sodium with an OH. OH is hydroxide, which is 1 minus, and Na, so this is sodium. There is a metal, and we know that its charge is always 1 plus, so we don't need the parentheses, and we don't need to change anything about the suffix. We just drop it in as is, so sodium hydroxide. So baking soda is made up of this species. Is there a metal? Yes, sodium. Do we know its charge? Yes, it's always 1 plus. We don't need parentheses here. What is the sodium paired up with? HCl O3. So HCO3, oh, right here is bicarbonate or hydrogen carbonate. So here we have it called bicarbonate, hydrogen carbonate. You'll see those used synonymously. I think now we use hydrogen carbonate, but for clarity's sake, I'll use bicarbonate. Or hydrogen carbonate. So baking soda is sodium bicarbonate or hydrogen carbonate. So this pillar in Delhi has been preserved over time, in part due to coatings, paint coatings on the pillar, one containing iron and PO4. PO4 3- is phosphate. PO4 3-. So if it is with one iron, then this iron must be iron 3+ for the charges to sum to 0. And so then the question, is there a metal? Yes. Do we know its charge? Not always, because it's a transition metal, but it's not silver, cadmium, or zinc, so we're not always sure about the charge. So in this case, we're going to have to use the parentheses and the Roman numerals to tell what the charge of the metal is. And because phosphate's 3-, we know the charge of iron must be 3+. And so this then is iron 3, and then phosphate. No changing the suffix phosphate, meaning it has more oxygens than phosphite will have, which will have less. So this iron 3 phosphate is one of the things that preserves this pillar in Delhi. So if our question, is there a metal, now that we've studied metals and we know which of them we have predictable charges with and which we do not have predictable charges when they form a cation, and what to do with Roman numerals in the parentheses for those species with a curious charge. What if the answer to is there a metal is no, there is no metal? Well, then we are going to be making a molecule which contain nonmetals only. And in this and only this case, will we be using the Greek prefixes mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. Only when there are no metals do we use prefixes to tell us how many of each of the element are there. It's tempting, once we learn how to use prefixes, to want to use prefixes for all nomenclature, but we're only going to use the prefixes when no metals are present. And the other rule that we should know, which will be applied here first, is that when the first element has only one species, rather than having the prefix mono, we'll have no prefix at all. The formula is prefix, name of the first element, prefix, name of the second element with that suffix "-ide" that's always present in our nomenclature, with the only caveat, if the first element is mono, we'll drop the mono. So here we have 1 carbon, but we'll drop that mono and just have carbon, and 2 oxygens, so di, oxygen, but we'll drop the suffix and replace it with "-ide", so oxide. Carbon dioxide. So is there a metal? No. Phosphorus and oxygen both are not metals. So we're going to use our prefix system. We're going to need the prefixes for 2 phosphoruses and 5 oxygens. So our prefix will be di, and then we just put the element's name in, so phosphorus. And then 5 penta oxygen, but we'll drop the suffix and replace it with "ide", so pentaoxide. Diphosphorus pentaoxide. Is there a metal? No, sulfur and oxygen, both not metals. So we'll use the prefixes. Does the first element have only one species? Can we drop the prefix? No, not the case. This time we have 3 sulfurs, so we're going to be using tri for sulfur and 9 for oxygen, so nona for oxygen. So we're going to be using the prefix tri sulfur, just drop the name of the element, and then nona oxide. Trisulfur nona oxide. And BF3, so it's like the next generation of BFF. Sorry, that's my joke. 1 boron, 3 fluorines, no metals. And so we have 1, we'll drop the mono for boron. So it's just boron, no mono. And then 3, we're going to use the prefix tri. And then fluorine, but with the suffix "ide", is fluoride. Boron trifluoride. So that is a simple overview of how to name ionic and molecular species, both when we know the charge of the metal and when we do not always know the charge of the metal, when we have polyatomic ions, or when we have molecules with no metals at all. So make sure you review this video and then go on to the assignment to help practice naming molecules.